Good morning all. Let's move for the next point, factors affecting the growth of boundary layer. In last lecture we have seen how the boundary layer is created. When fluid comes in the contact with the stationary body, the boundary layer is generated. At the boundary, velocity of fluid is zero and the gradually velocity goes on increasing and hence creation of the velocity gradients occur. And in that region boundary layer is created. Let's see the factors affecting the growth of boundary layer. The distance from the leading edge, the viscosity of fluid, the free stream velocity and density of fluid. These are the four factors affecting the growth of boundary layer. Moving to the next point, importance of boundary layer theory. It is used for calculation of friction drag of bodies in a flow. What is meant by drag, that we will see in the next part of this chapter. Calculation of pressure drag formed because of boundary layer separation. Answers of the important questions like what shape of body must have in order to avoid separation. This separation point also we will see at the last of this unit. Let's move for the next point, which is very important, called as boundary layer thickness. The velocity within the boundary layer increases from zero at the boundary surface to the velocity of mean stream asymptotically. Therefore, the thickness of boundary layer is arbitrarily defined as the distance from the boundary in which the velocity reaches 99% of the velocity of a free stream. Small u is equal to 0.99 capital U. It is denoted by symbol delta. The definition, however, gives the approximate value of boundary layer thickness and hence delta is generally termed as a nominal thickness of a boundary layer. The boundary layer thickness of greater accuracy is defined in the terms of certain mathematical expression, which are the measure of a boundary layer on the flow. The commonly adopted definitions of the boundary layer thicknesses are displacement thickness, momentum thickness, and energy thickness. Means, suppose this is a plate. Around that plate, let's say this is the boundary layer is formed. Suppose at this section the velocity is gradually increasing. Then from this point to this point you will observe velocity is different. Here the u is equal to 0, small u, and gradually that u goes on increasing, and at this point you will find u is equal to 0.99 multiplied by capital U. Means at this point the velocity of a fluid is almost equal to mean stream velocity. And this distance is nothing but boundary layer thickness and denoted by delta. This distance delta is the vertical distance as we have defined already. Hope you have understood what is meant by boundary layer thickness. Now it's time to move for the one by one the derivations for these three important terms: displacement thickness, momentum thickness, and energy thickness. First is the displacement thickness. It is very difficult to understand this definition by firstly reading, so you have to listen carefully and understand what I am saying. It is defined as the distance measured perpendicular to the boundary of a solid body by which the boundary should be displaced to compensate for the reduction in the flow rate as a count of boundary layer formation, and it is denoted by delta star. Let's see what is happening in the formation of boundary layer. In the figure A, you are seeing there is one plate. This is a plate. Fluid flowing from this direction, and due to that boundary layer is formed, and we have got at section AA velocity profile like this. If suppose we are using idle fluid, Idle fluid means what? Fluid which has no viscosity. If viscosity is not there, then there is no formation of boundary layer because the fluid will not stick to the boundary of a solid body. In that case, what will happen? For the same plate, velocity profile will be like this. Means everywhere there will be same velocity. Means for the same plate, let's say D diagram. In this D diagram, what you will observe that instead of having the curve at this point, which is let's say here A point, here is A point. If you compare between A point in figure A and A point in figure D, the velocity at A point is equal to velocity at B point, which is at the top. These two velocities are same. But in case of real fluid, velocity at A is not equal to velocity of B. Velocity of A is less than B. So you will observe that this much of part is lost in between section A and B. Means if you want to measure the discharge from these two sections, how we are measuring the discharge? Q is equal to area into velocity. Here if you take the average velocity, let's say U star. In between these two sections, average velocity is U star. And for the same area in the plate D where we are using idle fluid, velocity everywhere will be capital U. And U is always greater than U star. So what you will observe, Q in case of first plate and Q in case of second condition, that is D condition, will be different. Which will be more, A or D? In case of D, because area is same but U star is less than capital U. So due to that, what will happen? We are getting different discharges. If we are using idle fluid, we will get more discharge. If we are using real fluid, we will get the less discharge. We are having another condition. This. What we are doing? We are moving this plate. Whatever plate we are using in the example D, we are moving this plate in such a way that there is a compensation of a discharge. Compensation of discharge means what? If suppose Q1 is discharged at A and Q2 is discharged at D. What I want? Q1 is equal to Q2. How to make Q1 is equal to Q2? For that, we can't reduce the velocity in case of D. Instead of reducing the velocity in case of D, we are reducing the area of cross section by lifting the plate by distance delta star. If we lift the plate in such a way that Q1 become Q2, then what is Q1? Area into U star. Then Q2 will be equal to A2 into capital U. So what we have done, we have reduced the area by lifting the plate in upper side. And what should be the consideration here? The area of this section and this section, which is shown in the yellow color, should be same. Now let's see the definition once again. It is defined as the distance measured perpendicular to the boundary. This is perpendicular distance by which the boundary should be displaced. We are displacing the boundary to compensate for reduction in flow rate. So we are having the reduction in flow rate as we have discussed on the account of boundary layer formation. whatever reduction in the flow rate is happening due to formation of boundary layer, to compensate that we are lifting the plate in case of idle fluid. So that distance is nothing but displacement thickness. Hope you have understood the concept. Let's move for the next point. The definition we have seen, now we have to see the derivation. Let's see another definition. It is defined as the distance measured perpendicular from the actual boundary such that discharge through this distance is equal to the reduction in discharge due to boundary layer formation. Both the definitions are correct, any one will work. Let's see the derivation. First, consider u as a free stream velocity. Here u is the free stream velocity. B is the width of the plate. B is the width of plate which is inside the board. Consider a small elementary strip here. Here is the small elementary strip which has thickness dy at a distance of y from the plate. Let the velocity of fluid at elementary strip is u, small u. Means here you can observe boundary layer is formed. Due to that boundary layer, the velocity gradient is generated. Consider one section here, AA. At that section, here velocity is changing like this. From that plate at distance y, there is one small strip which has thickness dy. Now we have to calculate mass flow rate, which is nothing but mass flow per unit time through that strip. So how we are calculating mass flow rate? Q into density. Okay, Q is in meter cube per second, density is kg per meter cube. So meter cube will cancel and kg per second will remain. So to measure the discharge, we should know Q is equal to area into velocity. So considering this, rho is the density, area of strip multiplied by velocity at a strip. The area of strip is dy is the thickness, and inside the board we will have the width b. So area of strip is dy into b. U is the velocity at distance y. Let's say this is the equation number 1. If there is no plate, then fluid would have been flowing with the constant velocity equal to free stream velocity at section 1. Then mass flow of a fluid per second flowing through elementary strip would have been rho, area of the strip, velocity at strip when plate is absent. Means suppose there is no plate, only strip is there in the flow, then area is constant. We will get the equation rho multiplied by area is same, but what happened? U is converted into capital U. This is the mean stream velocity if plate is not there. Then this is the equation number 2. As capital U will be greater than small u, hence due to presence of plate and consequently due to formation of the boundary layer, there will be reduction in mass flowing per second through the elementary strip. U is always greater than mass flow rate in this case will be greater than mass flow rate in this case. So the reduction in mass flowing through the elementary strip is rho u b dy minus rho u b dy. So taking rho b and dy common, we will get the equation. So total reduction in the mass flow rate through the plate is nothing but integration of above equation. Integrating in between limit 0 to delta. 0 is the boundary where velocity is 0 and delta is the final boundary of a boundary layer. Here rho and b are constant. And let's see, this is equation number 3. So what up till now what we have considered, first plate is there. In the presence of plate, what is the velocity and what is the mass flow rate? If plate is not there, what will be the velocity and what will be the mass flow rate? Then we have seen what is the difference in mass flow rate, and lastly we have seen total reduction in mass flow rate flowing through due to a presence of a plate. Then last thing we have to do is that consider plate is there. Consider plate is there, but idle fluid is flowing and we want same discharge. Let the plate is displaced by the distance delta star and the velocity of flow for the distance delta star is equal to free stream velocity. Loss of mass of fluid per second flowing through the distance delta star. Now this we have to consider. Plate is there, idle fluid is there. We have to displace the plate in such a way that this yellow color area should be equal to this yellow color area. Rho into velocity into area means what we want to find out, the loss of this, the mass flow rate in this area. Mass flow rate in this area can be calculated by considering rho as a density, v is the velocity and a is the area of cross section. Here rho is same, u is the capital U is the velocity as idle fluid is there, delta star is the height and b is the width. So this is the loss of mass of fluid per second flowing through distance delta star. Equation 3, which was the last slide, in that last slide we have seen the reduction in mass flow rate, and this is also, this equation number 4 is also giving us the reduction in mass flow rate. So we can equate both the equation. This is equation 3 and this is equation 4. So what we will get by cancelling rho and b from both the sides, integration 0 to delta u minus capital U minus small u dy is equal to capital U multiplied by delta star. So delta star is equal to 1 by capital U 0 to delta capital U minus small u dy, taking u inside as it is constant 1 and making the simplification, we will get the final equation delta star is equal to 0 to delta 1 minus small u by u with respect to dy. In this equation small u is the variable and this equation is giving us the displacement thickness. I hope you have understood this concept. Little bit difficult to understand, but listen the things 2-3 times so that you will understand, and if suppose there are some questions, post on WhatsApp group. Thank you.